Welcome everybody. Today I want to talk about analysis. With the establishment of new bus systems and new network topologies, analysis comes more and more into focus. And today I want to talk about oscilloscope integrated solution for the data link layer as well as for the physical layer to do all analysis on one time base, preferable referred to the controller's time base. First of all, I want to explain the tool concept, starting with a part of a CAN bus. You see the CAN bus with the signals CAN high and low, and to get some traffic on the bus and send and receive messages, you need a network interface. The network interface has its own time base, optionally a time synchronization port, and interprets the data according to the protocol specification. In standard analysis ways, you have an analysis tool. There you can debug, trace issues on the data link layer, and you have also the possibility to establish complex test scenarios. But what is happening when we have effects on the physical layer and we have effects like ringing or crosstalk directly occurring on the cable? Normally we have to bring an oscilloscope into play. So far so good, but the oscilloscope has another point of view when analyzing the physical layer. It has its own time base, and analysis cannot be reflected to the controller's time base. So we have to do some issues to solve this problem. Let's start with a side of the controller. The controller sees CAN high and low and the diff signal, and it interprets the signal bit per bit and overlays the protocol data according to the specification for CAN or for other bus systems. So what does the oscilloscope see now? The oscilloscope sees the same signal, but time delayed. And the protocol data does not fit directly to the scope's measurement data. Now the goal is to eliminate the time base of the oscilloscope and to transform all scope data into the time base of the controller. Therefore, two prerequisites have to be fulfilled. First, we need an electrical connection between the scope device and the CAN interface, solved by synchronizing the synchronization ports by a sync line. And we need a dedicated trigger timestamp to reflect all further analysis on. With this knowledge, we can eliminate all delays, and the protocol data optimally fits to the scope's measurement data. Complex analysis is going underneath, but interesting is what the user sees from the analysis tool. Now he sees only the time base of the controller. Then he sees the protocol data here shown for the arbitration phase and overlaid with the scope measurement data. And you also get a detailed bit highlighting for each bit and the interpretation for CAN-FD or CAN if a bit is dominant or recessive. On the next slide, I will explain how we can get started with this concept. You need a standard PC where the analysis tool is installed on. You need an oscilloscope with a sync input and a CAN interface with a sync input, both connected via USB, and then both connected via stubs to the bus. Here you can see the trigger connection over the sync line with an Y-Y cable. And then we can get this system run. And additionally, we can bring a CAN disturbance hardware into play, also connected to the CAN bus. And we have the possibility to provoke errors on the physical layer as well as on the data link layer to prove the conformance of our ECUs or other effects on the bus. Now bring the trigger options into focus again. Trigger options are necessary to synchronize the bus interface with the scope hardware. All analysis is reflected to a dedicated trigger timestamp, and the common trigger timestamp is essential to eliminate the drifts, time drifts, caused by the transceiver delay of the bus interface and also caused by hardware drifts of different clocks. With this, we can overlay the physical data of the scope with the controller's data. And we have one point of view now. You have different trigger types for different bus systems, especially for CAN and CAN-FD. You have also the possibility to trigger on different waveforms, like on edges and pulses. And you have additionally different modes to trigger. You can trigger manually, take a snapshot of what's currently going on the bus. And especially you can trigger on protocol errors or on logical IDs. You can directly trigger on the identifier and do this in a loop. You have single mode or repeat mode. Now let's talk about some use cases, the most important use cases for this concept. You can directly detect the frames you want to trigger in your analysis tool, and then you can observe protocol errors. Very important for conformance testing against ECU specification. You can check the send and transmit behavior and your bit time settings. Additionally, you can prove the network design concepts, check your bus topology and the specification or the used cables and resistors. And you can also test the whole application through all layers and ensure data consistency. What's also important is to have an observer for EMC problems. For example, you have EMC problems if you have inductive devices in your network and you get effects like reflections, ringing, or crosstalk. Another important thing is that you have the possibility to establish your own test scenarios by using some methods like I-diagram or bitmask analysis. I will come up in detail later, or transition time measurement. You can measure the time of rising and falling edges. Now let's talk about a little bit in detail about analyzing, debugging, and tracing. Let's have a look into the tool. Here you see some tool windows. The slide is separated in 3 sections, starting from the left side with a data link layer. Then we come to the physical layer, consists of the frame layer and the bit layer, and the granularity of analysis increases from left to right. On the left side, you have a trace view observing all data coming from the bus. You see on which channel the frames occurred, and you see the timestamps of the frames. You also see which ECU has sent a frame. But if you trace error frames here and you don't know what's the reason, you have to go more into detail. So you have to go to the frame layer, shown here. And you can perform a first round trip. That means both windows are synchronized. You can measure the signal here, and you get a detailed bit highlighting of the bit sequence. And if you change your measurement cursors, it's also reflected in a more detailed trace view, where all frame parts of the entire CanFD frames are represented, starting at SOF, ending at the IFS sequence. And all analysis done in the frame layer is reflected to the logical layer, to the protocol layer. Is analysis on the frame layer not enough and you have to go deeper underneath? You can switch to the bit layer on the most right side and perform an eye diagram analysis. Here shown with the defined bit mask, the user can freely define a bit mask. At the moment there's no specification for CAN or CanFD bit mask, so it's a polygon you can free define. It serves a fit criteria to make you can determine the quality of your signal. And if you see the bit signals cross the bit mask, they will color red because they indicate an error case. A more powerful possibility is to use the programming interface of the tool. Here you can establish a more detailed test scenario. You can test bit per bit, shown here as the serial bit mask analysis, and you can perform another round trip. All analysis done in the bit mask analysis window is reflected here. You see all bits are shown serially, and each bit has a bit mask. Red bits indicate a bit mask violation, green bits indicate the bit is okay. I will explain in more detail on the next slide. And the last possibility is to control the eye diagram over the programming interface. So some additional analysis features: you can perform the analysis online during running measurement or afterwards in offline mode. Transition time measurement is possible, already mentioned. Then you can calculate the common mode voltage. It's automatically calculated, define min and max values of your boost signals. And you have also the possibility to create user-specific, application-specific statistics. Then you have some tools like measurement cursors acting globally or local in the shown graph view windows, and globally synchronized with other windows in the tool. To get some reproducibility, you have the possibility to export the session of measurement. You can export an entire measurement, or you can export the measurement data of special graphs like CAN high and low. And you can also export the eye diagram, which is replayed by import. Let's explain the bit mask analysis in detail and give an example for an automated test scenario. Here you see the program flow. First of all, in the first step, you have to define a bit mask. I will show. Here you see the green case. The first case is everything is all right. We have defined bit mask for each bit, for dominant bits and recessive bits. In the next step, a voltage dip occurred on the first bit, but it wasn't detected by the algorithm. Therefore, the algorithm extends your user-defined bit mask to the recessive and dominant bus level in the third picture shown, and then we can detect all bit mask errors in detail. Then you want to trigger on a CAN ID, or you want to trigger on a specific protocol error. You can wait in the programming interface until the condition is fulfilled, and then in the next step the analysis starts. The algorithm, as already mentioned, extends all bit masks to the recessive and dominant levels, and then determines if a bit mask violation has occurred in any bit. When finished, the results can be requested, and you get detailed information where a bit error occurred, when it starts and when it ends. And afterwards, you can archive your results in a dedicated report format. Here you see an overview over all test cases, which test cases have passed, which have failed. In this case, we investigated CAN and CAN-FD, and we investigated, for example, the data phase for CAN or the BRS bit for CAN-FD. Now I want to explain the eye diagram in more detail. On the left side, we have the configuration of the eye diagram. Below, the data history of the current measurement session. And in the middle here, we have the representation of all bit sequences. If you start eye diagram analysis, you can define some filter options on the left side. For example, which channel to observe and which bit sequence, the data phase or the arbitration phase. In this case, we observed the arbitration phase. What I wanted to point out is that all bits shown here are overlaid in an eye diagram, and you have an enclosed round trip. That means all analysis is logically connected. And here you see the eye diagram. Behind you have a bit legend starting with a sync field. Probably you cannot see now. Then TSEC1, TSEC2, and in the middle of both fields you have the sample point exposed here at about 70%. And you can directly prove your bit time settings of the controller. That means you can prove how good your rising edges will fit, for example, into the sync field. And now I want to show you that you can see both effects of arbitration in both windows. At the beginning of the arbitration, several nodes send dominant bits. Therefore, the voltage level increases. What you can see here in the frame layer, and you can see also here in the bit layer. And after the analyzed frame has one arbitration, the bit level decreases. Arbitration is completed. And this is also reflected in both windows. So now I will give you a real-world example with a variation of bus termination for a line topology. Here you see a line topology with 8 nodes. The line topology is terminated on both sides with 120 ohms. And during the measurement, we switch off one resistor and see what will happen. Therefore, we test a single and double-ended termination, and node 3 cyclically sends CAN frames. The eye diagram is depicted of the data phase, especially of the CRC field. And now let's read from the eye diagram what happened. First of all, you see some physically effects like ringing caused by changing the termination during measurement. But what is most important is that it takes much longer time until the edges cross the recessive level where the controller can detect if the bit is recessive than in double termination. The reason is the resistor increases, and resistor is directly proportional to the fall time, because a transceiver does not lead any current, and it behaves like an RC element when discharging. Here you see we have chosen a sample point at 85%. This was, the case was, we wanted both test cases run. If we would have chosen the sample point at 70%, what works for double-ended termination, we would have gained error frames in case of single termination. And the data phase transition rate was 4,000 kilobits per second. What I wanted to point out here is that you can compensate issues on the physical layer with an intelligent choice of bit timing to a definite degree to get or to compensate the issues. And it's normally not the intention to have a single terminated CAN bus, but I wanted to show the effects and how you can read the effects from an eye diagram. So now let's summarize the main points. The concept covers an all-in-one solution to analyze, debug, and trace issues for CAN and CAN-FD. Many use cases in automotive development profit from a common time-based analysis for the data link layer and the physical layer. You can prove your design concepts for ECUs or for different bus topologies. And you can perform a full round-trip analysis through all layers, starting at the data link layer, coming to the frame layer, then to the bit layer and back. And you have also the possibility to establish your own test scenarios running in a loop with a high degree of scalability and reproducibility. From my side, these are the main facts, and thank you for your attention. And
thank you very much. Do you have questions?
I'm David Wolander, Toyota Material Handling. A question about the eye diagram and the bit masks. As long as you don't get a violation of the bit mask, do you provide some kind of metric, like a margin to the bit mask, or is it just when you violate the bit mask you get the result?
you define a bit mask before analysis, and then we check if the voltage curves have crossed the bit mask, and then during the algorithm, we detect the bit mask violation. So.
Yes, but I mean, do you then, to find out how big margin you have in your system, do you have to adjust the bit mask until you find a failure, or can you from a given bit mask get a kind of a margin reading or something in your measurement tool?
I don't clearly understand, but can we get into detail afterwards?
Yeah, sure.
Okay.
Any other questions?
One moment, please. I already had a chance to test this tool. It was not fully implemented, so some features were missing, like the mask and so on. This was on the last Plugfest in Nuremberg.
Yeah.
And it's a great tool, so this is the first thing. And the second, when you showed these eye diagrams, Then you measure on the bus.
Yes.
This means the impact of the receiving transceiver is not measured.
At the moment, not.
At the moment, not. Now you could cover this by defining a mask that is more strict to cover the impact of the receiving transceiver. Or what is your idea how to cover the impact of the receiving transceiver? Because even if the eye diagram looks good, the communication may fail because the receiving transceiver may disturb the signal as much as...
Normally, we already discussed we have to establish a test matrix and we have to measure between every node, and we have also measure the receive pin, and the test scenario would be more complex, and at the moment we haven't implemented this, but that would be an outlook for future analysis.
Okay, so then we're done for this session. Enjoy your meals, and thanks to the speakers.